All right. So we had a little quiz last time, and I was asking if you want to email me your work. That's fine. And some people did, and they did a great job. So I want to start with this exercise where we clearly have infinity over infinity undeterminate form. And the topic of that section was to take a limit of your derivative of your numerator as well as derivative of denominator, right? So if I take the derivative of the top separately, this is going to be just number 2, right? Derivative of 2x, x is raised to the power of 1, so the remaining will be 0 power of x, so it's just 1, so 2 stays, and then denominator I'll have 2 the power of x multiplied by 4, that gives us 8, right? And then x will be raised to the power of 1, and when I take derivative of next term, it is 1. And this ends up being when I take a limit approaching to infinity, denominator will end up being unbounded infinity. And when I divide a fixed number by infinite, I end up with a 0. So that's our answer. Well, if you did not have a chance to do it, then do it. Do 10. If you want, you can do 8 or 9, whatever. It's pretty much same thing. So I guess that's nice portion of L'Hopital's rule you use when you take infinity and divide it by infinity. At least nowadays you could do this exercise the old ways, the ways Calculus 1 asked you to do it. If you had powers 1 on the top and power 2 on the bottom, then you can just divide by x every term on the top, so you'll end up with a 2 with the same thing. And if you divide by x every term on the bottom, you will end up with 4x, and 2 over 4x is still approaching to infinity. When numerator is fixed, it's 2, so it still be 0. So either way, it's the same answer. As always in mathematics, the answer is always the same. Right? So that was the idea of pretty much all the exercises here. So you take derivatives, and that's what we cared about. Now we actually utilizing L'Hopital's rule for the other cases, not just infinity over infinity or 0 over 0, but for the cases like in the exercise, let's say number 49, which is really not uh, 0 over 0, but it is analogous to 0 raised to the power of infinity. Because x approaches to 0, and 1 over x approaches to 1 over 0, which is infinity. So it is another, turns out, undeterminate form. And let me see, so is that 0 or is that infinity? What is that? If you try to just plug in 0, and you end up with something like that. So this turns out to be undeterminate form, and that's why you're gonna do a special approach to it. Use L'Hopital's rule, and the L'Hopital's rule will lead you to logarithmic start. So if I apply it to the right side logarithm, ln usually. Doesn't really matter what logarithm, what base of logarithm we use, but people always use ln because this is, I guess, favorite function in the and pretty much everywhere. So you take the property of logarithm or so-called power rule of logarithm, and that's the actual reason why logarithm was introduced. So we no longer have a power for the function, but we end up with 1 over x, which is multiplied by ln of x. So if I decide to take its limit, so if I take a limit, no, they want you to do the limits, right? So the limit when x approaches to 0, you will be able to use the L'Hopital's rule, and that's the whole point why we are here dealing with that. So ln x when x approaches to 0 and 1 over x. Please notice this is going to be, what about ln x? Remember the graph of natural logarithm function. Ln x is given domain only positive values of x. For domain, we don't have any negatives. X is strictly greater than 0 because it's defined only for the portion of coordinate plane to the right from our y-axis. So only on the right side. And that's the reason why they actually say limit when x approaches to 0 on the right side, which means here, because on the left side, there is no function, it is undefined. So someone may start wondering, why is it a plus here? Well, to make sure that we're dealing with defined portion of logarithmic function, because otherwise it's not going to work. So please notice that we have here infinity, right? And x approaches to 0 when x goes to 0. When you say infinity, well, when we get closer to 1, it is actually negative infinity, right? Negative infinity. Let's see, so what should I do? Can I use your L'Hopital's rule if it's infinity over 0 or what? Well, so it looks like you need to prepare this a little bit. So this way you will be able to take your derivative because you divide in infinity by 0. But remember, you could always prepare this in a different format because let's say if you have, let me write it here. X approaches to 0, right? And the top is infinity. So what I can do is write it as 1 over x, which is approaching to infinity, right? So when x approaches to infinity, this reciprocal approaches to 0, then reciprocal to infinity, or vice versa. If reciprocal is 0, then itself it approaches to infinity. So you can always flip. So what can I do with that? Because I want to really try to have this somehow turn into infinity or 0 over 0. So if I put instead of 1 over x my infinity, it's not gonna work. So maybe I can somehow change it. So if it's 1 over x, that is gonna be put in where? In numerator and in denominator, or where should I try? Like, for example, if you have one, like before, ln of x is also approaches to infinity. Okay. So 1 over ln then will approach to 0, right? So somehow I need to rewrite this expression in such a way that infinity or 0 or 0 to the L'Hopital's rule to take those derivatives. But, right, so how can I do that? Well, for example, if you take your x in denominator, that is 0, right? So if you put this as 1 over x, so that's still approaching to 0, but notice that's going to be if that's 1 over x approaches to 0, start like that. When 1 over x approaches to 0, then x will approach to infinity. So I'm trying to rewrite it as a fraction, right? And the fraction should have infinity over infinity or 0 over 0. So I use my L'Hopital's rule to be able to work out the indeterminate form. So I'm preparing. So if that's 1 over x, so x goes to 0, then 1 over x goes to infinity. And then ln x is going to be itself infinity, right? I'm going to say, well, if both of them are going to approach to infinity, 1 over x and x. So I end up with infinity times infinity, which is infinity, isn't it? You see what? Well, let's say you have a number that approaches to, let me say y, so you don't get z, approaches to infinity. And you multiply it by z squared. Well, that's also approaching to infinity, right? So what about their product, z cubed? Well, it is also approaching to infinity. I don't need that. So let's see, what is that we produce here? I was trying to cross it out, but better just erase. So the point of the story that we have here, infinity, and if you multiply it by 1 over x, which is infinity, the product is actually infinity. And that's the point of this exercise, that you have ended up with the limit, but please notice it's not limit of the function you want, it's a limit of ln of y, right? Which is infinity. Right? When x approaches to 0, we have ln of y worked out like that, and it's ended up with infinity. So what about y itself? Well, how can I write this as a ln? Well, it turns out if I can apply ln to e to the power of y, or e to the power of ln of y, either way, you're gonna end up with what you need. So if you, maybe I will go e to the power of ln of y. So you can write it like that, or you can write it like that. Did you know? It's the same thing, because bases in both cases will be e. So that's going to be infinity. So anyways, if ln of y infinity, then what about e to the power of ln of y? Well, that's e to the power of infinity, which is infinity. Looks like that's the result. That's worth to think about, and maybe I can do another little exercise because it's something that deals with this play with ability to take ln and find the answer, and then you convert it back to the function you need, and to convert, you either write it as ln, or I think that's better, e to the power. So if we know that ln of y approaches to infinity, you end up with replacing ln of y as infinity, e to the power is the result. But I wasn't careful. It is negative infinity. Why? Well, because remember this little minus that I lost here? So it's end up being negative times positive. The result is negative. Oh, now I see where I forgot. Minus. And that's going to give you a big deal because it's 1 over e to the power of positive infinity. And that's going to be 1 over infinity, which is 1 over big, which is small. It is actually 0. Sorry. So the answer for exercise number 49 is 0. Because of negative sign. So infinity, but with a minus sign because it went down, right? Didn't go to the right. If it went to the right, yes, but it was approaching to 0. So the result was negative infinity for the 1 over, and for the logarithm, and 1 over gives you infinity, and infinity times negative infinity was negative infinity. So e to the power of negative infinity is going to be actually approaching to 1 over big, small, to 0. Let me do one more, I guess. Maybe I can do another one here just to enjoy. It looks like this is pretty much the same. Oh, that one was not 0, but infinity, right? So maybe you can think of it if you feel like it, but I can do something with a ln. Let me try 57. 57 with a ln. That looks a little different. So let me try 57. Please notice that I did not really use L'Hopital's rule here. I didn't differentiate, right? I just utilized this approach of taking logarithm. I say, what kind of exercises are those? They're not integrals. No, it's totally different. It's limits, right? So we don't use integrals, but in the next section we will. So don't worry. In the next section we will, of course, enjoy some logarithms. So integrals. So in 57, I have the x that approaches to 1. See, it is important to think of where x actually goes to. And if they say 1 on the right side, well, it is all about defining. And of course, we can check out y, but it's not really going to participate anywhere. So you have ln x, and now this ln x is raised to the power of x to the power of minus 1. Please notice that this is not something that I can apply a special power rule for logarithm. Like I cannot bring 2 in front using the power rule because the 2 goes down, because this ln is squared. So if I have ln squared of x, that's not the same, it's different. So for that one, I don't have a property because I have just the product of ln x times ln x. So it's not the power times, but it means ln x times ln x. And since we have the whole thing is raised to the power of x minus 1. We don't know how many times ln x we need to multiply with itself. Let's say if x is equal to 5, then it'd be 5 ln's, or if x is 6, it's 6 ln's multiplied. So it is not the same. That's what they're showing us by placing these parentheses. So that's something to watch out. So you cannot use the power rule for logarithms, but you can do exact same thing we did in the previous. So if I say I'm trying to take limit of y, which is whatever we have here, ln x raised to the power of x minus 1, then I can take care of this x minus 1 if I applied ln once again on both sides. Okay? If I apply the lens on the left as well as on the right side, then I can use the power rule for logarithms. And say it'd be ln of ln. Well, we don't really care what it is. If needed, we can always take the derivative, and that'd be derivative taken by the power rule, right? The chain rule, chain rule. We can apply chain rule to it. But the point of story now, I have no power. Ooh, okay, great. So now I want to see what the limit is going to be if my x approaching to 1. Remember the limit we are trying to find here, but x is sent to 1 for what? Well, looks like it's going to be ln of x. Well, remember, I just tried to graph ln of x. So when we approach into 1, on the right side, on the right side, as they say, we're approaching to 0, right? So that's approaching to 0. Now, why is it so important? Why cannot it approach it to 1 from the left side? And now we'll see why, because of domain of the function logarithm. It does not participate, though, in the solving exercise, but just to make sure. Notice the values of function will be negative, right? Here, negative. So you need to take ln of, if that's negative, then we're in trouble because we are applying function ln to negative if it's a minus side, if it's left side. And if you apply ln to something negative, well, look at the domain of function ln. And if you try to apply it to something negative, it is undefined. So it's always sign here plus or minus or plus, because they want to make sure that it is in domain, otherwise it's undefined. But we don't utilize that, so don't really care. But that's the reason why they will be placing that plus. So anyways, if you have this x, which is approaching to 1 on the right side, x minus 1 will approach to 0, right? Okay, so this piece approaches to 0, and that's ln 0, and ln of 0, we already saw ln of, actually, it approaches to 1, so it goes to 0, but when you are applying ln to it, then this whole thing is going to, use green color. This stuff goes to infinity. So it's 0 multiplied by infinity. So we end up with another undetermined form, 0 multiplied by infinity. And somehow I was able to work this out. And the question is, how? Well, I need to write it as 0 over 0, if possible, or infinity over infinity. And if you're going to think about 1 over something. So if that goes to 0, then I need to somehow pull this to infinity. So let me get some room for that. So rewrite my expression. So I think that now I will be trying to use derivative, because in the previous exercise, we ended up with infinity times infinity. Remember, one was positive infinity, the other was negative infinity. 1 over x was positive and that ln was negative, so I had to multiply and ended up with negative infinity. So I didn't really have to do L'Hopital's rule. But now I ended up with a 0 times infinity. So I think I'd rather just leave my logarithm untouched, but instead of multiplying by x minus 1, I will put 1 over x minus 1 in denominator. So I divide by reciprocal. So when I divide by reciprocal, I can multiply by, flip this, by x minus 1, and that will be my x minus 1. And that stuff is still here. And this is something that I can work with. So it's ln of x. So why can I work with this again? Because of L'Hopital's rule that will be applied to infinity, ln of 0, infinity. It is again negative infinity, to be careful. And 1 over x, 1 over 0 is infinity. And this enables me to take derivatives. And I will enjoy taking it, because now I can take derivatives of ln and that be 1 over x, and that's what's going to make me happy. So it looks like now I'll be able to differentiate, and I need some room for that matter. So this stuff is not needed. So let us take derivatives. So now I'm using the thing that we learned last time, the L'Hopital's rule. So let me do it again. See, the problems are getting, even though it seemed to be nice, but well, I just need to be a little bit more careful. Because the derivative of ln is 1 over, and that's ln of x, because my outside ln is taken care of by that derivative. But then the chain rule comes into play, and I need to multiply it by derivative of ln of x. It's 1 over x. So that's taking care of my top. Okay, what about the bottom? Well, the bottom, I don't want to write it a lot of times, but I can do it on the bottom here. So it's the bottom on the bottom. So it's x minus 1 to the power of negative 1, right? So I'm prepared to do differentiation. So now I take derivative of my denominator. Let me take care of that derivative, and this is also differentiated. And the point of story is I need to be careful with the powers. I know some people just do that in their head right away. So negative 1 comes out, and that x minus 1 in the parentheses will become raised to the power of negative 1, subtract another 1. Power rule for derivatives. And for that matter, I can write it as a 1 over x minus 1 squared. So I get a little worse situation with my, and the minus here, so it gives me the whole thing negative. So I got my denominator worse, and this is, right, minus 1 over x minus 1 squared. But my numerator does not have ln of ln, right? So what can I do at that stage? Well, maybe now I need to prepare it to rewrite it again before I can differentiate again if I need. let me first of all prepare it. So my x approaches to 1 on the right side. It's still on the right. It's always going to be on the right side. So now I can flip my top. So that becomes x minus 1 squared, like that. And the bottom, which is going to be x times ln x. You see that the ln kind of disappeared. And please notice that now we have x approaching to 1. So this fraction is going to 0, right? This 1 minus 1, 0, positive. And what's here? Well, x goes to 1, so what's the ln of 1? Well, the ln of 1 is 0, right? So it is 0 over 0. So I should be able to take derivative once again. And then I will decrease my power of x once. And if I take derivative once again, I'll decrease my power of x second time. So that way I will be done. See how lengthy this exercise is? I need to keep taking derivatives. And I guess I'm going to need to move for some more room and do derivatives. So as I said, some problems here are in the textbook are really taking the time. And well, some people may try to find the other way around, but I'm not sure if you'll be able to. But I think it's always a good idea to try, because again, your way of tackling the exercise is always the best way if you do it yourself. So the second part of this section is definitely something, right? Compared to just taking derivative of top and the bottom. But again, it's nice, it's 0 over 0, so I differentiate. So let me continue here. And at most, there'll be 2 steps, because when you do the derivative here, it'll be 2 times an x minus 1 itself, right? Power of 1. Notice that if you take derivative of x minus 1, it's just 1, because chain rule. So it's already first power. But now for denominator, well, we have derivative of product. So it is getting complicated on the bottom, but as I said, we don't care. We'll just write it. So it's like f times g, remember? Derivative of product, f prime g plus g prime f. I think it's good to refresh calculus 1 ideas. So if your function f is equal to x, and if your function g is equal to ln of x, then what about other 2 ingredients in this setting, f prime and g prime? Well, f prime will be derivative of x, and that's our favorite. It is 1. And g prime as derivative of ln of x is 1 over x. So set it up. F prime is 1, right? Instead of g, I put ln x plus g prime, which is 1 over x multiplied by f prime g prime f, sorry, why did I put that? F prime g prime f. So what's the function f? That's x. So please notice that we ended up with ln of x plus 1. Okay. So I took derivative of my denominator and ended up with ln x plus 1. Before to differentiate again, I need to be always careful. I need to check and see if that's in undeterminate form. Well, that goes to 1 minus 1, 0. And the ln of 1 approaches to what? Also 0, right? See, really? Well, graph of logarithm. At 1, we're approaching to 0 when we get closer, right? So, okay, so we're still able to differentiate, because if you're not able, it's not 0 or 0, it'd be wrong to do derivative, but now we'll be done. That's great, right? Great feeling that almost done. So it looks like I have 2 left over on the top because derivative of x is just 1. And then ln of x is going to be 1 over x. Okay. So this is as if I took limit. Let's see, should I flip? Well, you could just plug number in. So it'd be 2 over 1 over 1, which is 2. When x approaches to 1, right? That's great. We done with another exercise. So L'Hopital's rule is being used, and looks like it's the only way to, I guess, do the exercises here, and it is indeed something. So maybe over weekend you can try to go over exercise 57 or try another one in here. And I think I may just go over another exercise with you. This looks like it is something definitely new. So, oh, that they worked it out in here with a sine of x. Sine x over raised to the power of x. So what they can do is take derivative of sine. So notice with trigonometry. So 0 to the power of 0 in determinant form, because sine x, when x approaches to 0, is going to be 0. Is that right? Well, graph of sine will tell you. Function sine is indeed at 0. This is 0. If it's approaching to infinity, you wouldn't be able to do anything because it's just bounded between -1 and +1. But in the case when x approaches to 0, your x gets closer to 0, and y coordinates fall down and go to 0 if it's on the right side. Or on the left side, doesn't matter. They have it on the right side. Let's see, why on the right side? Well, because ln will be involved to make sure that we have no problem with the domain. So anyways, they apply ln's to both sides, right? So that's first thing, and then they take the limit and see what comes out. So when they apply ln, they bring that x again in front, and then they have x times ln. So if they put 1 over x on the bottom, just like we did with the previous exercise in here, they end up with something that approaches to infinity on the bottom and negative infinity on the top. And why is it negative? Well, because it falls down. Okay, so it looks like it's pretty much the same thing, right? And then they take derivatives. So now you need to take derivative because 0 infinity over infinity. So derivative of 1 over x is negative 1 over x squared, just like we produced. But here you use some trigonometry. So derivative of ln is 1 over sine. Derivative of sine is negative cosine. So cosine over sine is cotangent. So you get that thing. Interesting. And then they flip cotangent, so it becomes tangent, and flip 1 over x squared, it becomes x squared. And then they prepared it to differentiate it again. So I guess it's worth to notice that twice, or like we had here, 3 times differentiations are possible, and then we're pretty much done. So it is interesting in a way, but it is tedious. So they do have problems starting at 45 and a little bit tedious side. So maybe I'll do one more in here next time. I guess it's too much. It's getting a little bit too much, right? With this, maybe something else for a change. So for a change, it's pretty straightforward section. and here that deals with improper integrals. So it turns out that sometimes, so maybe I'll clean the mess. Stop share. Share. And move to the next section. We'll just start. We'll do more exercises first next time. So the idea is you cannot integrate if your limit is infinity. So if you're trying to find a limit from 1 to infinity, how are you going to plug in infinity? You can definitely find antiderivative. So if you try to find x power of -2 by the power rule for antiderivatives, if you try to add 1, right? If you integrate, you're going to end up with, and then 1 will be -2. So -2 plus 1 is -1. So it's going to look somehow like that, right? Antiderivative. And the problem is you cannot really plug upper limit, because you can plug 1 definitely, but no upper limit, right? Let's see, what is this? It's like -1 over x. But what they notice that the problem with plugging in that infinity for the upper limit is solved. So what they do is they say, put a b instead of upper limit. Instead of infinity, they just use any letter. They're like b. Say why b? And you just use letter b. And take limit when b approaches to infinity, because they cannot just plug infinity. They say, but 1 over infinity is like a 0. Well, technically, yes, but they work it out formally. So they say that 1 over infinity turns into 0, this 1 over big, 0, small, and all you're left with is whatever is here, and that 1 is going to be plugged in -1 over 1, but since the lowest is subtracted, lower is subtracted, so it becomes positive. So anyways, that's the idea. So once you took antiderivative, then to be careful not plugging in infinity, even though you do when you work out the limit, you kind of say 1 over big is small. But formally, they just put 1 over big, which is, I guess, not really something very tricky. So let us try to do an exercise with this infinity like setting. How about 21, for example? So once again, I'm going to take it as a limit when b approaches to infinity, but I don't want to put the infinity as my value of limit. So I'll put from 1 to b. And now it becomes integral that I can take, and after I took the integral, I will calculate limit. So that's the plan. So this be 3x to the power of cube root is in denominator, so it is -1/3, right? Okay, dx. And then I take antiderivative here. So 3 will stay. X will be raised to the power of 1 plus 1/3 is 2/3, right? And I put that same 2/3 in denominator. Okay, that's great. And that's from 1 to b. And I take a limit. See, what's annoying is to now write all this structure, limit and stuff. But just write it nicer. Looks like now I'm going to be flipping my fraction on the bottom. So it becomes 3 halves, and times 3 will be 9 over 2, right? And here. And then what else is left? Looks like b will be raised to the power of 2/3, and I know that 2/3 is a cube root. from something squared, right? So that's b. And then I will subtract cube root from the lower limit square, which is 1. Okay. So this is our limit we need to take when b approaches to infinity. What is that? Well, cube root of b is approaching to infinity, right? When b goes to infinity, then this guy will approach to infinity. So from infinity, you subtract 1, and it is still infinite. Multiplied by 1/2, it is still infinite, so it is infinitely large. It is infinite. Isn't it? So sometimes it is infinity, sometimes it is something finite, and you can always decide when you're taking your limit. Now, what about if I try 31? Looks like it's arctangent, isn't it? Remember, if you trig substitution, maybe I'll do that one and that'd be good enough for today. So first of all, notice there are 2 infinities. So how can I work that out? Well, I can say that we take a limit when b goes to infinity, and now it's going to be integral from minus b to plus b. Or you could split this into 2 integrals, but it is the way to take care of this infinities structure, right? And then what? Well, looks like then I need to recall the fact that when I want to deal with arctangent, okay, let me write this whole thing down first. So it's still 4, right? And then divided by 16 plus x. Okay. Trig substitution, right? Identity, or actually what have to deal with that formula for trigonometry. Well, let us refresh our memories how we take antiderivative in terms of trigonometrical approach, right? So I need to recall that if I do have du, so it's a formula here. If I integrate, I think we already saw this back in the beginning of this class. So that's a squared plus u squared. Right? So you don't have to use any substitutions, basically, just d on the top. And arc tangent, right? And now the only place to watch out is that 1 over a is coming out. And when you take arctangent of arctangent, u over a. So this is something one needs to have access to the table of antiderivatives. We already used it a few times. So it looks like in this case, our a is 4, right? 4 squared. Okay, so for a equal to 4, we end up with 1/4 arctangent of x over 4. So antiderivative is not hard to find. And just to end this story, because we need to do definite integral minus b to b. So now I need to use, I think, one little fact about function arctangent being odd. So if I recall the graph of function arctangent, which varies, so tangent goes like that, and arctangent and it is having horizontal asymptotes, 5 over 2. So it repeats itself, but since it's a function, then we disregard the other process. So arctangent and the asymptotes. So the point of story, this is the odd function. What does that mean? So if you take your plus b and minus b, the pieces will be the same. The areas will be the same, but they will cancel each other out. So plus and minus b is going to give you 0. And when you take the limit of 0, you're going to get 0. Let's see, really well, just put in arctangent b over 4 and arctangent b over 4, subtracted the negatives. That will looks like give you the cancellation, I think. That's interesting, right? So we'll do more of these antiderivatives next time, because turns out the improper integrals help us to work out the cases when upper and lower infinities, but also cases when we get so-called vertical asymptotes. So because the approach into infinity here to the right is one thing, but we could also approach to 0 if we move to the top, and this is also going to be unbounded integration. So let me try to find a picture. They very famous for producing nice pictures. Where's the picture of that case? Oh, where is this? Here it is. So the case when you have between 0 and 1. So notice that at 0, value of function is becoming infinity. So if you try 0, then what you do, you actually cut it someplace. And that place, they like to call it as letter B. Again, they send to 0. They send it to 0. So they can plug in b again as usual, so that we find it integral, but then they see what the limit will be when b goes to 0, which is analogous procedure. We'll do it next time. I think it should be enough for today, and I think I will maybe ask you to set up the analogous antiderivative. Next time is a little quiz. I think it's a little bit too much for today for the quiz. It's, I know, very getting too much, so I'm going to stop recording. But next time we'll have a little quiz on this, just for you to practice. So anyways, I